Welcome to the Calculus C section. So when dealing with improper integrals, more often than not we're actually concerned with the value of the integrals. Welcome to the Calculus C section. In this section we'll be discussing the comparison and integral tests. So when dealing with improper integrals, more often than not we're not actually concerned with the value of the integrals. We are more interested on whether the integral is convergent or divergent. So in order to address this ordeal, we use the comparison test or the integral test. So we will give this test for a subcase of the infinite interval test. However, versions of this test exist for other subcases of the infinite interval tests, as well as integrals with discontinuous integrates. So the comparison test is as follows. So if we have f of x, which is greater than or equal to g of x, which is greater than or equal to 0 on an interval of, we said, alpha to infinity, then if the integral of f of x dx from those same intervals converges, then so does the integral of g of x with the same interval. So essentially what this is saying is, if we have a miscellaneous function, we'll say 2x, which is obviously greater than x, which is still greater than 0, and we're saying that hypothetically, we're not saying these functions do converge or diverge. We're saying that in the event that 2 of x converges, x has to converge because it obliges by the same patterns that 2x does, because all 2x is 2 times x, and that means that x is just the same function. This is just a scalar, which means that if this function converges, then so does x. So now, in the second scenario, we're saying that if the integral of g of x on the same intervals diverges, then so does, oh my apologies, this should be f of x. And that is true because, for the same reason, we're saying that now we know that 2 of x is greater than or equal to x and is greater than or equal to 0. We know that this function, we'll say that this function diverges. We're saying, okay, this function is going to reach infinity. So because x is a similar function to g of x, as we're stating in this scenario, then this function is going to have to diverge as well. So now we're going to move on to the integral test. So the integral test is actually more simple than the comparison test, or it's actually very variant based on how you like to see things in math. So we're saying in the integral test, if the integral from infinity to k, which are our two regions or bounds of f of x, converges, then so does the series that we're dealing with. So we're saying that we'll have x squared, and we're saying our sum is actually the infinity n equals k x squared, okay? And so our function, we're saying that if the integral of that function converges, then that same series is going to converge. So in the same way that if we said that x squared diverges, that in that same series, if we took the integral and x cubed over 3, it actually diverges, then that series diverges as well. So I hope that helps and gives you more insight as to the test that we use to test convergence and divergence for series, and there is a lot more information on the website. I hope that helps.